Jnanam paramam dhyayam. Knowledge is supreme.
So, let us look at is this V1 V2 form a basis? Let us look at R2. Okay. V is R2. Look at the vectors V1 is 1 1, V2 is minus 1 minus 1. In R2, right, if we have two linearly independent vectors, then they will form a basis, right. The dimension of R2 is 2, 1 0 0 1. If I am able to find any two linearly independent vectors, right, they will form a basis. Are these two linearly independent? I can easily check. Yes, what is one way of doing it? Simplest way is found the determinant, right. Look at the determinant. When are the either rows or columns, whichever way you like, right. For a square matrix, when are the rows or columns independent? If they are independent, then it is invertible, right. Then it is invertible. So, it is a 2 by 2 and invertibility is determinant is not equal to 0. So, for 2 by 2, 3 by 2, 3 by 3 is not very difficult to check via determinant. So, that is the advantage of determinant, checking directly whether something is independent or not for simple things computation. So, these are independent because determinant is not 0. So, let us fix T of V1 is 1 0. Okay. So, we want to find check whether what we have done. I want to fix T of V1 as 1 0. So, V1 V2 are basis elements, T of V1 is 1 0, T of V2 is 0 1. Okay. I want to know what is T of a general vector. So, how do you compute V of a general vector? For any V, I should write first it is a linear combination of the basis elements. V should be written as sigma alpha I V I and then T applied to it, and then T of V I is we know. So, let us do that. So, if we look at x y, okay, so it is x plus y by 2 times V1. So, that is a linear combination of V1 and V2. You can check any vector, okay, x y, this is a linear combination. Okay. So, what is T of this? It will be x plus y by 2 T of V1 plus y minus x by 2 T of V2 by linearity. That is what we are saying earlier. So, if you do that, what is T of V1 is 1 0, T of V2 is 0 1. So, it is this scalar multiplied by the vector 1 0 plus y minus x by 2 multiplied by. So, what is this? X plus y by 2, x y minus x by 2. So, that is the linear transformation. So, it says once I fix the values of T on the basis vectors, every other vector, because it can be represented uniquely as a linear combination of the basis, T of that will be linear combination of the T of the image vectors of the basis vector. So, that values we know, so we can compute, right. So, this is given images on the basis elements you know, how to find the general formula for the transformation, right. So, is okay. Yeah, this you have to do the linear equations, right. X y is equal to alpha V1 plus beta V2. So, you will get two equations in two variables, you have to solve them. So, basically that previous knowledge will be coming handy here now. You want to write a vector as a linear combination of known vectors. So, x y is equal to alpha times 1 1 plus beta times. So, you will get two equations in alpha beta in terms of x and y, right. X and y are fixed for you, given to you. So, find the value of alpha beta in terms of x and y. So, that is how you check whether a given vector is a linear combination of some other vectors or not, right, solving a system of equations, right. So, this is obtained by solving two equations in two variables alpha beta. Okay. So, here is a important theorem which will prove. It says we are associating with the linear transformation some subspaces. T is a linear transformation from a vector space V to a vector space W. So, look at all the vectors in the domain which go to 0. Look at all the vectors u in the domain u belonging to V such that T of u is equal to 0. All the vectors in the domain which go to the 0 vector, collect them together, that set is called kernel of the linear transformation. So, what is the kernel? All the vectors which are killed by the linear transformation which go to 0. So, in the domain collect together all vectors whose images are 0. So, that is a subset at present, but the claim is actually it is a subspace. So, what is the difference between a subset and a subspace? It is a subset of obviously of all u which go to 0, but if u1 and u2 go to 0, then u1 plus u2 also should go to 0 and alpha times u also should go to 0. It is a vector space, right. So, we will prove that. So, this kernel is all the elements of the vector space V which go to 0 is called the kernel. The range, like range of a map, right, the image set. So, what is the range? Range is T of u, u belonging to the domain, that is the range of a function as it is, right. So, claim is if T is linear, then the range also is a vector space, okay. Second and third, now kernel T and range T both are vector spaces. So, they will have dimensions. So, it says dimension of kernel of T plus dimension of the range of T is equal to dimension of the domain space V. This formula holds. This is same as this dimension of the kernel is called the nullity actually, and dimension of the range is called the rank of the linear transformation. It is same formula that we had for rank nullity theorem for matrices. We will see how it is related to that also later on. So, it is same formula, okay, same theorem for linear transformation, that the rank, right, dimension of kernel is the nullity, dimension of the range is called the rank. So, rank plus nullity is equal to dimension of the domain space n, right. So, let us prove this theorem, okay. Proofs are quite simple, straightforward. So, let us prove them. So, I will write the proofs so that it is easier to understand slowly. So, the first one, T is from V to W, right. So, what is kernel of T? That is equal to all u belonging to V, say that T of u is equal to 0. So, as such this is a subset of V, right. So, claim kernel of T is a subspace. So, to prove this, so let us take let u1 u2 belong to V, kernel of T, take two elements and take scalars alpha and beta belonging to scalars, take a linear combination, then alpha u1 plus beta u2 should belong to kernel of T. That is what we have to show, right. To show it is a vector space, a linear combination of elements should be inside. So, let us to show this, what is to be shown, that this element also has the property T of this element is 0. So, let us note T of alpha u1 plus beta u2, what is that equal to? Linearity plays the part. So, it is T of alpha u1 plus T of beta u2, but again by linearity alpha comes out, it is T of u1 plus beta of T of u2, right. I am using linearity. So, this is equal to alpha times this is 0 plus beta times 0, because T of u1 belongs to kernel, u2 belongs to kernel. So, T u1 is 0, T u2 is 0. So, this is equal to 0, right. So, that proves that the kernel is a subspace, right. Let us look at the range, whether the range is a subspace or not. So, let us look at the range. So, what is range of T? What is this? These are all W belonging to W in the image such that W is equal to T of U for some U belonging to V. Is that okay? Right? All the points in the codomain which are images of something. Right? Another way of saying, this is another way of saying it is T of U, U belonging to V. Both are same. Okay? This is equivalent of both of them. So, this is a subset of W. Range is a subset of W. Claim W is a subspace. Right? So, what do I have to check? So, let W1, W2 belong to W, alpha and beta be scalars. So, to show alpha W1 plus beta W2 belongs to W. So, let us, how do you show that? I should represent this as T of something, as image of something, right. So, note, so this is what we, so alpha W1 plus beta W2, what is that equal to? We know W1 is in the W1, sorry, I wrote W, right, I should have written as T of U. W1, W2 in the range I should show, right. The other one is always true, that if two elements are in W, then linear combination is W, that is a sub vector space anyway. But to show that the range is a, so here was the mistake, W1, W2 belonging to the range, right, should imply the linear combination is also inside the range, right. That is what is to be shown. So, let us start with this one, W1 belongs to the range, that means what? Alpha 1, what is W1? Some T of U1 plus beta, what is W2? It is some T of U2. So, where W1 is equal to T of U1 and W2 is equal to T of U2. Is that okay? Because they are in the range, they must be the images. So, what does this give you? So, this is equal to, implies that this right hand side is alpha of T1. So, I can write as T of alpha 1 U1 plus T of, why did I write alpha 1 anyway, it does not matter, there is no alpha 1, there is alpha only, right, plus beta times U2. This alpha can be taken in because of linearity, beta can be taken inside because of linearity, and that is same as now linear is alpha U1 plus beta U2. But this is a new element in U, right. So, that means W, that means alpha W1 plus beta W2 is a image of some element, right, using linearity, nothing more than that, we are not doing anything, just using what is given, use linearity and bring it inside. So, it is a subspace, right. Okay. So, let us look at the third property, the third thing we want to show. We want to show that the dimension of kernel of T plus dimension of range of T is equal to dimension of V. So, T is from V to W, keep that in mind, right. So, let us say this is dimension n and this is dimension m, right. V is a vector space, it will have some dimension n, right, W will have some dimension m. So, just put some, so that we do not have to write everything. Okay. So, now we want to compute what is the dimension of kernel. How does, what is the definition of dimension? What is the dimension of a vector space? It is the number of elements in any basis of the vector space. If the dimension is n, right. It will have some n vectors as there is a basis for it, we do not know what it is, we can find. Let us start. So, let kernel of T have basis. Kernel of T is a subspace, right. So, it is a vector space in itself. So, it has a basis, right. So, let us write have a basis. So, let us call this as V1, V2, Vk, k less than or equal to n. Is that okay? This kernel is a subspace of Vn, right. So, it will have some basis, let us say k elements are the basis, dimension is k, right, and this k will be less than or equal to dimension of Vn, because it is a subset of Vn. So, k less than or equal to n. So, I just a picture, imagine this is V, right, it does not look like, I am just Venn diagram I am trying to show, and here is your kernel of T is a part of it, right. So, kernel we have taken as a basis, but the whole space also has a basis, right. So, what we are trying to do now is enlarge this given basis of kernel to a full basis of V. I can go on adding more and more non-zero elements, right, till I get n elements which are linearly. See, because if kernel is not whole of V, there must be a vector outside, right, there must be a vector which is not a linear combination of elements of the kernel. So, add that to the basis of the kernel, you get one more k plus 1, probably that itself fills it everything. If not, take one more and add till you get n elements which are linearly independent, right. So, what one says is enlarge it to a basis of V, enlarge it, that means you are given k vectors which form a basis of the kernel, add how many more you will be adding, n minus k, so that you get n vectors which form a basis of V. So, enlarge to a basis of V1, V2, Vk. Up to here this is kernel, the new ones which are added is V k plus 1 up to Vn, you get a basis of V. Is that okay? Right. Okay. So, this to form a basis of V. Okay. So, the whole thing has got a basis. Okay. Now, let us look at, so consider any W belonging to range of T. Let us take any W belonging to range of T. That implies W must be equal to, if I is in the range, it must be image of something for some U belonging to V. Is that okay? If W is in the range, it must be image of something. Now, I have got a basis of V and U belongs to V, right. So, now this U can be written as, I have got a basis for V, U is element of V. So, what should I have? That means, now there exists some alpha 1, alpha 2, alpha n such that U must be a linear combination of the basis elements. Here is the basis element, right, for this basis. So, it will be alpha 1 V1 plus alpha 2 V2 plus alpha k Vk plus alpha k plus 1 Vk plus 1 plus alpha n Vn, right. It is a linear combination. So, U must be written that way. But what I am interested in is, I am not interested in U, I am interested in W, because I want to get a basis for the range. So, I should go to the image. So, what does this imply? What is T of U? So, implies what is T of U? This linearity. So, it will be alpha 1 T of V1 plus alpha 2 T of V2 plus alpha k T of Vk plus I am using linearity again and again. Alpha k plus 1 T of V k plus 1, okay, plus alpha n T of V n. Using linearity and using u is a linear combination, T of u must be a linear combination of the images, right. So, that implies what is T of u, that is W, right. So, W is equal to what is T of V 1, here is V 1, where is V 1, these are form a basis of the kernel. So, what is T of V 1, 0, T of V 2 is 0, up to T of V k they are all 0. So, let us use that fact, this is 0. So, this goes off, this is not required, this is not required, they are all 0. So, what is left is alpha k plus 1 T of V k plus 1 plus alpha n T of V n. So, what does it mean? Any vector, so implies any vector W which is in the range is a linear combination of these ones, right. That means, the range of T is span of the vectors T V k plus 1 T of V n, right. These vectors span. Only thing we have to check now, if they want to show is the basis, once you have got a set of generators, you want to show it is a basis, what we should do? Prove it is linearly independent, right. So, claim is that T of V k plus 1 T of V n are also linearly independent. So, let us check that. So, how do we check they are linearly independent? Same, a linear combination equal to 0 should imply all is equal. So, let us say beta k plus 1 T of V k plus 1, I am choosing purposefully the betas now, right, plus they are arbitrary, beta n T of V n equal to 0. What is to be shown? To show beta of j equal to 0 for every j, all these betas are 0, right. But if this, now what do we know? We only know that these V k's are independent, right. We know something about, you recall, because we had a basis, these were the basis of V. So, these ones are independent. We have to now somehow go back to the domain space and use this fact there. So, how do I go back? So, the idea is this one, okay. So, let us look at the left hand side of this is equal to, okay, I add to it T of V 1, T of V 2 and T of V k, all of them, because they are all 0, right. So, it says sigma, let me write beta I T of V I equal to 1 to n equal to 0, okay, for any beta 1 up to beta k. Take first k any beta 1 beta k, but T of V 1 is 0, T of V 2 is 0, T of V k is 0. So, those first k terms will be anyway 0, whatever be beta 1 beta 2 beta k, right. Remaining this combination is given to us, right. This is given to be equal to 0, is it okay? So, implies linearity now, take linearity, that means T of sigma beta I V I equal to 1 to n is equal to 0 by linearity. I am going back now. So, that means what? T of something is 0, that must be in the kernel, right. So, implies sigma beta I V I equal to 1 to n belongs to kernel of T, right. But they were for any beta i's, okay. So, what does this imply? what is the property of V1, V2, Vn? They were a basis, right, and I have got a linear combination now, right. So, this belongs to kernel. So, that means what? So, that means what? What is our aim to show? That beta i's are equal to 0, right. So, they belong to kernel of T. Okay. Take a linear combination which is equal to 0 to show this is equal to 0. So, this is okay. Oh, okay, okay, okay. Sorry, I shouldn't be hurrying through. So, let me just from here let us rewrite what we want to show. To show that beta is okay. So, let me write it again. There is a simpler way of doing it. Given beta k plus 1 T of V k plus 1 plus beta n T of V n equal to 0. I want to show implies all of these are 0, beta k plus 1 equal to beta n equal to 0. That is what I want to show, right. Okay. So, let us show this. Okay. So, this one implies that T of beta k plus 1 V of k plus 1 plus T of beta n V n equal to 0, right. Linearity. So, let us bring again linearity, that means sigma of let me write sigma beta j V j, j equal to, it has gone off somewhere. Okay, let us come back. V j, j equal to k plus 1 to n equal to 0, right. Now, that means this element belongs to kernel, right. T of something is 0. So, that element must be in the kernel. So, implies sigma j equal to k plus 1 to n beta j V j belongs to kernel of T, right, from k plus 1 onwards. But I know that kernel has got a basis already, V1, V2, Vk. So, this element must be a linear combination of V1, V2, Vk. So, implies sigma j equal to k plus 1 to n beta j V j must be equal to sigma alpha I V I, let me write okay, j here, I equal to 1 to k, right. Now, bring everything on one side. So, what does that imply? So, bring everything. So, implies that minus sigma alpha I V I equal to k plus 1 to n plus, pardon, oh, I equal to 1 to, sorry, 1 to k plus j equal to k plus 1 to n beta j V j is equal to 0, everything on one side. Now, what is the left hand side? Left hand side is a linear combination of V1, V2, Vk up to Vn, all of them, but I know that is linearly independent, all of them are linearly independent because they formed a basis of the whole space V. So, implies what? All the alpha is equal to 0 equal to beta j for every I and for every j, all of them must be 0 because V1, V2, Vk n were independent, right. So, implies that T of, so what we have got is T of Vk plus 1 T of Vn is a basis of the range T of u, right, that is equal to range. So, basically the idea is we start with a basis of the kernel which is in V, enlarge it to a basis of whole of V, whatever you added there, the first are k are in kernel. So, their images will be 0, they do not contribute anything. The idea is that the remaining n minus k will contribute to the range of T, they will be independent and everything will be generated by them. So, how many are there? N minus k, right. So, dimension of the range space is n minus k, nullity has got dimension k. So, total is equal to n. So, that is the rank nullity theorem. Basically doing what? Looking at a basis of a kernel, enlarging and saying the images of the remaining ones which you have added form a basis for the range, that is all. Okay.